Support vector machines. We've looked at logistic regression and see that it is a linear classifier because it has a linear kernel. But if we wanted to build a linear classifier from scratch, mathematically the most natural thing would have been to produce what we're now going to see, which is a support vector machine. Let's remind ourselves about logistic regression with large beta. Essentially, we're looking for where the kernel is positive for positive patterns or classes, and where the kernel is negative when we have a pattern that is in a negative class. There are only finitely many training patterns, so we can choose a lambda that's between 0 and the smallest possible absolute value of w dot t sub j. So therefore all the w dot t sub j's are greater than lambda when t sub j is a positive, and all of them are less than negative lambda when t sub k is a negative. So let's let omega be w over lambda. Then omega dot t sub j is greater than 1 if t sub j is a positive, and omega dot t sub k is less than negative 1 if t sub k is a negative. And this is true for any beta, so we're especially interested where beta is going to infinity and we're getting the activation as a step function. So now we're going to redefine w, the parameter vector, to be beta times omega. And then across all possible omegas, what we're looking for is where w dot t sub j greater than 1 if t sub j is positive, and w dot t sub k is less than negative 1 if t sub k is a negative. So that means that linear separation is equivalent to two separating hyperplanes. Positive above w dot x equals 1 and negative below w dot x equals negative 1. Now what we're going to use this for is to find a unique separating hyperplane, and in some sense the best separating hyperplane. We saw last time that there are infinitely many possible. And the hyperplane, of course, is again going to be where w dot x equals 0. So let's look at an example in 2 dimensions. So remember our bold x vector here is 1, x1, x2, and therefore w is w0, w1, w2. So there w dot x equals 0 is a linear function. x2 is a function of x1. If in particular if w2 is not 0, then we can solve for x2 in terms of x1. Notice we get a slope and a y-intercept, and therefore this w dot x equals 0 truly is a straight line in our 2-dimensional example. So what is the distance between where w dot x equals negative 1 and w dot x equals 1? Again, we're doing this in 2 dimensions, but it works in any number of dimensions exactly the same. That's one of the beauties of vector spaces. When you're working with 2 vectors, you're in a plane no matter what dimensional context you're looking at, because 2 vectors determine a plane. So notice that we can think of w here as perpendicular to w dot x equals negative 1, because it's perpendicular to w dot x equals 0, because w dot x equals 0 means orthogonality. We're going to find d to be the shortest distance between the separating hyperplanes. If we've got a u which is on the positives hyperplane and a v which is on the negatives hyperplane, and we draw a vector in between, then we can see that d is going to be the length of the side for which u minus v is the hypotenuse. And we call that the projection. And you can actually show that the projection of u minus v onto this vector w is w dot u minus v over w dot w times w. Again, we'll use some linear algebra in our explanations, but you're not required to know linear algebra. But it is nice because it makes these calculations pretty straightforward. Now notice w dot u is 1 and w dot v is negative 1. So therefore the projection is 2 over the norm of w squared times w. So we take the distance then, and we get d is 2 over the norm of w. So now we have a new problem. If we want to maximize d, that's the same as minimizing the norm of w, because d is equal to 2 over the norm of w. So that's going to be subject to a couple of constraints. W dot t sub j greater than or equal to 1 if t sub j is a positive. W dot t sub k less than negative 1 if t sub k is a negative. Now notice only a subset of the training data actually matters. So the data, the ones that are a long ways away from these hyperplanes, they really don't play any role. The same thing with the zeros. If the zeros are a long ways away from these hyperplanes, they don't really matter. So the ones that matter are called the support vectors. So we've got the training data now, t sub j, y sub j, and we're going to change. So we've got y sub j equals 1 if t sub j is in class 1 and y sub j equals 0. And we're going to notice that we can rewrite w as a linear combination of the t sub j patterns. So we've got t sub 1 to t sub r. These are the patterns that we're actually using to determine the hyperplanes, to teach or train the support vector machine that we're eventually going to have to recognize different classes. Most of the time, these a sub k's are going to be 0 because the a sub k's for t's that are far away from the hyperplanes, they don't matter. Only the ones that are close to the hyperplanes actually matter. And that's why we call these support vectors. Now I have a whole lot of them circled here, but in reality, we're going to see later on, there's only 3 support vectors in this two-dimensional example. So we've got training data where y sub j is equal to 1 if t sub j is in class 1 and y sub j equals 0 otherwise. And our goal is to find these coefficients a1 to ar for which w has 3 properties. W dot t sub j is greater than or equal to 1 if t sub j is positive. W dot t sub k less than or equal to negative 1 if t sub k is a negative. And the norm of w is as small as possible. The margin is the region between w dot x equals plus or minus 1. And the width of that, as we saw, is 2 over the norm of w. And the vectors, again, for which the a sub j's are non-zero, these are called the support vectors. So let's see how this works. So we've got this support vector machine problem, and we're going to use SVC out of sklearn because this is the Python support vector machine. And what I'm going to do here is use the support vector machine classifier, and I teach it the data. Notice there's only 3 support vectors, but we do get this division into 2 regions. And there's our margin. And notice we have the 3 support vectors, and the margin is the region that's determined essentially by the line through the zeros and then the line through that 1 that's parallel to it. So there's only 3 support vectors, even though we sort of indicated a lot of them. Okay? So what if it's not linearly separable, however? So we could use what are called soft margins, which allows a few data points to be in the margin region. But now we've introduced some arbitrariness into the problem. How many is too many? How soft is too soft? So linear support vector machines find the best separating hyperplane for a linearly separable classification problem. It reduces the size of the training set because all we need are the support vectors. But there's a trick, and that's what we're going to use when it's not linearly separable.